Okay, everyone, so we're going to start chapter 3 with this discussion, this lecture today. So, chapter 3 is going to be about atomic structure. That probably is going to scare you guys a little bit, but it's really not that difficult. What we're going to be mostly talking about and what I will be mostly questioning you on will be electron configuration. So, this is just going to be a little introduction as to light, what that is, because it does play an effect on electrons and how they move, which is important for us to know, and how all of these discoveries were made. So, first thing is going to be light is known as electromagnetic radiation. Okay? So light has a lot of different things. We're not just going to see it within the visible spectrum. Light also exists outside of that. So that's why it's called electromagnetic radiation, because electromagnetic radiation is formally defined as any form of radiant energy in the electromagnetic spectrum. So what is the electromagnetic spectrum, right? I said that word, right? Well, do I know what that is? Well, it's a possibility that you do. Of course, I threw that in the wrong spot. So, there's a possibility that you do. The visible lighting spectrum is included in that. But there's also some other spectrums as well. So, the electromagnetic spectrum includes a continuous range of radiant energy that includes gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, and radio waves. So it occurs as such. So 10 to the 16th, negative 16th, 10 to the negative 10, and to the negative 8. It's about 10 to the negative 6 or so, okay? It's a little bit in between there, 10 to the negative 6, 10 to the negative 4, 10 to the negative 2, 10 to the 0, 10 to the 2, and 10 to the 4. Okay? So down here is going to be our gamma. We go from here to here. It's going to be our X-rays. So that's a pretty high frequency. They're pretty tiny, right? Really tiny light wavelengths. So that's why we easily can get X-rays and gamma rays to go through our body. They practically have no mass. They have very, very small wavelengths, so they can go through pretty much everything. We've also got ultraviolet. That's the bad stuff, right? You talk about it all the time. What the sun gives off. That's right after X-rays. Okay? And then we hit the visible. So this is the visible spectrum. So this is going to be 400 nm, 450 nm, 500 nm, 550 nm, 600 nm, 650 nm, 700 nm, and and 750 nm. And that just goes essentially from RGB. So purple to red. That's how it goes in the visible spectrum. And the transitions in between. So purple to blue, blue to green, green to yellow, yellow to orange, orange to red. Okay? And in between you get different shades and such. But that's essentially how it goes, and that's what each one of these wavelengths is about, where it's at. The next part, if we go from here to here, this is going to be the infrared. Okay? And this is kind of important to spectroscopy. So a lot of spectrometers that, detect things and measure different quantities will use the infrared spectrum. The next is going to be the microwave. And this is what is used. You can't see it, right? But this is what is used in your microwaves. Right? Can you see that? You can't. So therefore, that's where this comes into the spectrum. It's not visible. Visible is here. This is where we see colors. This stuff, not so visible. And then the last one's going to be radio waves. So think of it. FM frequency, AM frequency. Those are following within the radio waves. And they're much bigger, much longer. They travel longer distances. That is why. Because they are the highest wavelength out of all of these. Okay? So each of those numbers that I talked about within this spectrum are basically wavelengths. And the wavelength is defined as such. And that's the formal letter for wavelength. It's like a weird number. So the distance from crest to crest. Or you can say trough to trough. Of a wave. So if I'm drawing this, I'm drawing my waves, okay? I'm going to go like this. So the wavelength is from here to here. So where my start and where my stopping point is, okay? So from here to here. Everybody understand that? That's going to be my wavelength. So think about it, 10 to the 100 meters. So hectometers, kilometers. That's how long those waves are for the radio waves. That's why they can travel such distances, that we get to them. Because most times, whenever you're listening to the radio, especially if you're listening to an FM station and don't listen to digital radio, that is actually traveling all the way from a specific station. I believe that we have one, 96.9 is located in Lancaster. But I can get that all the way out in Philadelphia. So, you understand that they're traveling quite a far distance. The next part, that's the difference. So, when I talked about AM versus FM, I said the word frequency, right? So, frequency. So, the number of crests of a wave that pass through a point of reference per second. Okay? So this is going to be comparing this to this. Okay? This one is going to have a greater frequency than this one, but this one's going to have a larger wavelength than this one. So we get AM radio stations much further than FM radio stations. Which ones do you think has the higher frequency? Well, it's FM because AM is much further traveled, so it's got a longer wavelength. So that's closer to like the kilometer side. Um, the AM radio stations are closer towards the 10 to the hectometer side. Okay? So, and these are going to be measured in hertz, which is going to be our SI. Remember that? SI, unit of frequency. Okay? So this information is important because they use this type of information, measuring the frequency, measuring the wavelengths, to determine certain points of the electron. The electron's a much smaller thing, but it is still an electromagnetic wave. It travels in a wave-like pattern. And so because of that, we are able to come up with different models of how an electron travels. So if we remember what we discussed when we talked about our different scientists, and our big points in atomic theory, we remember the name Rutherford, right? Okay, so Rutherford, after he discovered the nucleus, came with a model of the atom. So after he did his gold foil experiment, which he had actually his, assistants do, but he still takes the credit. So after he did that, he theorized that the electrons travel around the nucleus. Okay, so my nucleus is positively charged, right? And my electrons would travel as such. There's some problems with this theory. What is the biggest problem? Likes attract unlikes. So, negative wants to go to positive. So, his big problem was positive and negatives attract. So, if his theory was correct, the atom's unstable. If his theory was correct, the electrons would go straight into the nucleus and start bombarding it. And we've already discussed that you don't bombard a nucleus with electrons. You bombard it with neutrons. So, his theory is not correct. However, it did give some people the certain platform that they needed, specifically Niels Bohr, to produce the correct model of the atom that we use in today's society and today what we use for our class today. And his is a little bit different. So Rutherford could never specifically state why the electrons never went and attacked the nucleus of the atom. Bohr theorized using a bunch of math that is explained in your book, and if you want to read it, go ahead. I'm not going to question you on any of that kind of stuff. But Niels Bohr theorized that the atoms were confined to specific energy levels, and that contained different shaped orbitals. So, that sounds a little complicated, okay? So, Bohr's model of the atom. So, he says that there's atoms confined electrons to specific energy levels that contain different shaped orbitals. Okay? So that's what Bohr said. He was like, well, they don't do that, so there's got to be a mathematical reason behind it, did a bunch of math, and figured it out. So his model looks a little something kind of similar to this. Now, it's much more complicated than just this, but this is the idea. So this is my nucleus. I'm going to color it in. I have one energy level. It's called n equals 1. And then I have a second energy level, n equals 2. And so on and so forth. So this basically stated that these electrons had to stay within their energy levels. They couldn't just go and attack the nucleus anymore, like Rutherford's model stated. They follow it in a specific pattern in a specific orbital around the atom. Okay? So, this led to a couple different discoveries. So, big discoveries are going to be quantum theory. However, there are some other minor ones we're going to talk about real quick. So, he discovered that there were ground state electrons. Okay? And this is the most stable. Lowest energy state of a particle. So this is where we want to go. Okay? Remember, think about grounding when it comes to your typical outlet, right? You have to have a ground on your outlet now. So a way that if something happens where you get shocked or something shocks or anything like that, it automatically cuts off. So that's what this kind of thing is. It's the same similar level. We have a ground state for our electrons, and that's where they're stable. They don't want to move. They're not energized. They're not crazy. Okay. So then we get to what we talked about before a little bit was the excited, right? So obviously, if ground means neutral, they're fine. They don't got energy. They're good. They're all happy. This is going to be excited state. Okay, so this is going to be the energy state above the ground state. Okay, so it could be different levels. There's different excited states, but we don't calculate those. We just call it an excited state and leave it alone and call it a day. And that's going to basically state that the electron is excited, wants to move, wants to do something. It's not stable, wants to go to this ground state, so wants to give off some energy. Remember when we talked about gamma radiation and how that nucleus was excited and it went down and gave off a gamma ray, and then it was just back to a normal unexcited state, ground state. That's where these discoveries came from. Thank you, Niels Bohr. So, the third is going to be an electron transition. So, this is going to be the movement of an electron between energy levels. I just want you guys to know the definition of this. I'm not really that concerned with you knowing when an electron's going to transition between energy levels. We use it as we use it a little bit in electron configuration, but I'm not going to ask you those types of questions. That wasn't something that I even studied myself until I got up into my upper levels of chemistry. So with this, basically what it's stating is if that electron's in an excited state in an orbital that it's not supposed to be into, or an energy level that it's not supposed to be into, it wants to go to the lower energy level. It wants to go to the ground state. So it's going to go through an electron transition. So if it's at the excited state of energy level 3, but there's an open spot in energy level 2, it's going to go through an electron transition to get to that energy level 2. That is what this is, essentially. So now we're going to talk to the fun part, quantum theory. So quantum theory is basically a lot of fun math that you're not going to have to do, that basically tries to determine exactly where an electron is at any given time. So this is going to be known as our quantum numbers. So there's going to be 4 of them. So it's one of 4 related numbers that specify the energy, shape, and orientation of an in an atom. Okay? So you're never going to have to calculate quantum numbers. I'll give you those quantum numbers. You just have to know what's acceptable quantum numbers and what's not. So, first quantum number is our principal quantum number. So, this is going to be N, and it determines the energy level. So these numbers will always be whole numbers with the exception of the spin quantum number, which will be 1/2 or plus -1/2 or plus 1/2. But they will always be whole numbers, and it will never be 0 for principal. Principal will always start at 1, then go to 2, 3, 4, 5, 6, and 7 is the highest that we have. I'm sure we'll get higher once we make bigger molecules. So the next one, so we've determined what the energy level is. Now within each energy level, there's a different orbital. So that's going to be determined by the angular momentum. Quantum number. And this is given the letter L. So, determines the shape of the orbital. Okay? So, is it going to be an S or P or D or F? And that is what we will discuss probably in the next portion of this video. The third one is going to be the magnetic quantum number, and this is given M sub L. So this determines the orientation around the nucleus. I.e., like if you're going in the X direction, the Y direction, or the Z direction, because it is three-dimensional. We are three-dimensional guys, so it is three-dimensional. And then the final one is going to be the spin quantum number. So, and this just determines the orientation of the spin of the electron. Either 1/2 or -1/2. Those are the only two numbers that you can get for that one. So both the angular momentum, both the angular momentum and the magnetic quantum number will be given either negative or positive numbers and include 0, but they will all be whole numbers. So -1, -2, 0, 1, 2, 3. Those are numbers that are acceptable for your magnetic and angular momentum quantum numbers. However, your spin quantum numbers is only going to have 2. It's -1/2 or +1/2, and that's it. So if you see 0 or something written for your your spin quantum number, your MS is what it's going to be, M sub S, then it is not correct. It is not an acceptable quantum number. You cannot use it. So I'm going to stop this video here, and we'll continue with what are acceptable possible quantum numbers that can be used within our system of quantum numbers. Okay?